Assalamualaikum and hi. In this video, we are going to learn about state versus path functions in thermodynamics. So when we talk about a given system, we say it is in a particular thermodynamic state. So this term, a particular thermodynamic state, is characterized by a few macroscopic observables. These macroscopic observables, it is something that we can measure, something that we can actually see. For example, the pressure, temperature, the volume, the color, the altitude, and other things. Now, let's look at some of these differences or changes in macroscopic observables. And I'm using pressure, volume, and temperature as an example. So what we have here first is the delta P, or the changes in pressure, which is equal to the pressure at final minus pressure at initial. This is similar for volume, where we have the same formula here. The differences for volume is equal to the volume at final minus volume at initial. This is same goes for the temperature. The changes in the temperature is equal to the temperature at final minus temperature at initial. Now, what we would be able to say about all of this? And for just thinking about the initial and final state, for the change in pressure, change in volume, or the change in temperature. So what can we say about all of these examples? So in each case, we are going from initial to final, We are calculating in difference, and one thing that we can say that it doesn't matter how that system arrived at the final state from the initial state. The only thing that matters is that the difference. So we are going from some initial pressure to the final pressure, and it doesn't matter if we go slowly or we go quickly. All that matters is that the change in the pressure is the same. We can say the same thing about the changes in volume and also the changes in the temperature. And this is basically the definition of a state function. It just means that it only depends on the current thermodynamic state of the system, where it started and where it arrived at, and how the system attained that state. It doesn't matter. So another example is the compression of a gas inside a piston. So this is the delta V example. Here is the V initial, and we can either push the piston slowly or we can push quickly. But the bottom line is, if we are going for the same final volume, the delta V is going to be the same regardless of which path we use. So these are some other examples of state functions. So the change in internal energy is a state function. So delta U here, or sometimes can be written as delta E, is a state function. Some other state functions is a big one that we are going to talk about, the unit, which is the enthalpy. The enthalpy, delta H, is a state function. So it only depends on the initial and the final state, not how you get there. So this delta P, the changes in pressure, the differences in volume and changes in temperature, the altitude, the mass, and also chemical composition. These things are the examples of state functions. So from the previous slides, we have learned about the state functions. And from that state functions, I've already mentioned the term paths, but there is a path functions, or we call, other than the path functions, is also being called as a non-state functions. They are functions that depend on the path taken, getting from the initial state to the final state, and we call those path functions. So it does depend on the path followed in getting from the initial to the final state. So that means it does depend on whether you go all around circling a house or you just go directly to the house. It does depend on the paths, so you will get different value for your answer depending on the path that was taken. Later on, I will show you the examples for these term path or non-state functions. Two path functions that we have are work and heat. So work and heat are the examples of path functions. And an example kind of way to think about it is if you have two ice climbers of equal mass and they are going to scale this ice cliff. So one of them is really good at it and he just climbed right up the cliff. And the other one here is more of a beginner and he has straps in so that he doesn't get hurt. But he is going up a little bit, but then he backslides. Goes up a little bit, backslide a little bit more, might rest on this, might rest on this ledge, for a little while, and then goes up some more. And so the bottom line is this beginner climber is end up spending a lot more energy or doing a lot more work to get to the top of the cliff. So that's the difference between a path and a state function. In a state function, remember the altitude, for instance, it only depends on where you start and where you end. So that will be your state function. But for this cliff, where the two ice climbers, one of them who just goes directly up and another who backslides a lot, they are going to have different amounts of work. And the work is a path function. So I'm going to go through a similar example of state function in this slide. If you look at this, let's imagine here that somebody is hiking all the way up to the top of the mountain. And in this case, the hiker can either choose to go through path 1, which is the blue path right here at the side of the mountain, where it goes straight up. And then the other path in red color here, which is path 2, is to go through this more scenic route where the hiker is going through zigzag path all the way to the top of the mountain. Now, if you look at this example right here, you can take a look at two different things here. One is just the altitude, which is basically the difference in height that the hiker would have when he's at the top of the mountain versus when he's at the bottom of the mountain. So when he is at the bottom of the mountain, the altitude will be 0 feet, while when he is at the top of the mountain, we assume that the altitude of the top of the mountain is 10,000 feet. Now, if you look at the altitude of that hiker when he's at the top of the mountain, here, his altitude is always going to be 10,000 feet, regardless whether he goes through path 1 or whether he goes through path 2, because he is going to end up exactly at 10,000 feet higher than what he was when he was starting. In other words, the altitude is not affected by the path that this hiker takes. Now, think about what's affected by the path that this hiker takes. Clearly, the distance traveled is affected right by the path that this hiker takes. If he takes this direct path, he only needs to travel 5 miles. For instance, let's say this path 1, the distance is 5 miles, whereas if he takes this path 2, then he should travel about 12 miles. So as you can see in this example, there are certain things, certain properties like altitude for instance, that is not affected by the path that the hiker takes, and there are other properties on the other hand that is affected, whose values affected by the path that a hiker takes. Now, we can then take this back to thermodynamics. It turns out that there are functions in thermodynamic properties, whose value doesn't depend on how the system or the path that the system takes to get from the initial to the final state. And there are also properties of the system whose values will depend on the path that the system takes from the initial to the final state. Therefore, this is the difference, or how can you differentiate the term state function and non-state function. So for non-state functions, the work done by the hiker will not be the same if he chooses to take different paths. For example, the work done by the hiker the value will not be the same when he took path 1, and the work done by the hiker will not be the same if he chooses to take path 2. Now, when we are doing calculations, calculating state functions is a lot easier than calculating non-state functions. To calculate the altitude of this hiker when he's at the top of the mountain, the only thing you need to know is where he is starting from and where he's ending at. You only need to know 2 numbers. For example, I need to know the number here and the number here. And then I will subtract one number from the other, and I will just get the change in the altitude of the hiker. However, to get the value of distance traveled, it is not enough for me to just know where this hiker is starting and where he's ending up at. I need to know exactly which path the hiker takes. In other words, I need to know every little detail about or which way did he go. Did he go through path 1 or did he go through path 2? And I have to make these measurements throughout to determine how much distance that this hiker covers. Clearly, to calculate the value of non-state functions, you are going to need a lot of information, whereas to calculate the value of state functions, you are going to need less information. And that is always good, because if you need less information, that means you need to do fewer experiments. You don't need to do as many measurements, and yet the number you get is still useful. And that's the power of state function. That's kind of the idea of state functions, that when we can measure something without really knowing the details, that is really useful because it makes our life a lot easier. So that's all for now. We'll see again each other soon. Thank you.